Hi, I'm Mike Seaman with Eta One Power, and today we'll use Eta Designer to create a PWM controller module that can be used in any of our projects. We'll explore the creation of subcircuits and use the new analog and digital controller blocks to create a custom controller. In this video, we'll create a voltage mode synchronous buck controller. Start by placing a new subcircuit on an empty schematic, then double-clicking on it. Choose Edit Subcircuit to edit its schematic. We'll start by editing the subcircuit's parameters. We can give the subcircuit a descriptive name, such as voltage mode PWM. If you're modeling an IC controller, you can place the part number here. This window gives us the opportunity to add parameters to the subcircuit. These parameters can be easily edited in instances of the subcircuit. We'll add a parameter for the frequency of the PWM. We'll name the parameter freq, representing switching frequency. We'll set the type to a floating point type with a typical value of 300K. Set the minimum to 100K, the maximum to 1 meg, and the units to hertz. Okay. Now we'll define the controller. We'll delete the default circuit and add the ports for our controller. We'll start by adding an input voltage pin, name it VN, and set it to a power input. Then, add the ports for the compensation network. We'll start by adding one called FB for the feedback input, set to an analog input. Next, we'll add the port for the error amplifier output, called comp, and set it to an analog output. Then, we'll add the ports for the gate drive output. We'll add one for the high side output, called HO, and set it to a digital output. Then we'll add another digital output for the low side gate, called LO. Finally, we'll add a ground port, called GND, and set it to a bidirectional power port. The next step is to place a complementary gate driver for the two gate drive ports. We'll place the module and wire it up. This module will automatically create the necessary dead time between the two gate drive signals. Then we'll define the clock and PWM ramp. Place a pulse source and double-click to edit it. We'll use the parameter defined earlier to set its period, so we'll enter 1 over freq as the period for the pulse generator. The pulse width will be set short, like 10 nanoseconds. We'll make the period visible on the schematic. The next step is to place a variable ramp block to create the PWM ramp. The variable ramp block allows us to create input voltage feed forward by making the ramp proportional to the input voltage. Hook the pulse generator to the reset pin to define the frequency, and then connect the input port to the ramp generator. We'll set the slope multiple of the ramp to 0.1 times freq, and the maximum ramp value to 5. An initial or reset value of 0 is good. We'll show the ramp rate on the schematic. The next step is to define the compensation block or error amplifier. We'll place an op-amp. We'll connect the feedback port to the negative pin of the amplifier, and then connect a reference to the positive pin. We'll use a step voltage source as our reference to incorporate a soft start functionality to the controller, mimicking a number of controller ICs. An initial value of 0 volts is good. We'll set the final voltage to 1 volt and ramp the voltage up over 200 microseconds. So that's our reference. The output of the error amplifier will be connected to the comp port and will connect to an external compensation network. We'll then create the logic at the heart of the PWM controller. Start by placing an SR latch to control the input to the gate driver block. We'll then turn on the PWM output at each period, so we'll connect the set pin to the pulse generator. Next, we'll add a comparator to determine the turn off of the high side gate. Wire the output of the comparator to the reset pin. Connect the positive comparator input to the PWM ramp and the negative input to the error amplifier output. This connection will turn off the gate when the PWM ramp exceeds the error amplifier output. Just like that, we've defined the internals of our PWM module or subcircuit. We can close this window and a message appears asking us whether we'd like to update the subcircuit symbols to reflect the port changes in the subcircuit. Click Yes to update the symbol. These new pins are shown based on the ports we've defined in the subcircuit. Now we just have to move them to reflect the desired appearance and layout of our controller symbol. I'll expand the symbol outline to fit our pins. Press the R key to rotate the pins as needed. It's always good to place relevant pins adjacent to each other to make the external schematic as clean as possible. Now that we have the symbol defined, we can close the window. So here's our defined controller IC. We can double-click it again. Here you see that we can edit the switching frequency parameter of the subcircuit and also select whether to save internal simulation data for the module. Let's now see how we can make a library from the subcircuit and include it in our other designs. We'll again edit the subcircuit by clicking Edit Subcircuit. We can export the subcircuit in the library menu by choosing Export Subcircuit or Export Flattened Subcircuit. The first option will simply create an editable copy of the subcircuit as shown, which can be placed directly in schematics. Exporting a flattened subcircuit will condense the subcircuit into a single element with its internals hidden from its users. In this case, we'll just export the full subcircuit. We'll now just name our library with a simple name we can find later. The library we've just created simply contains a single element here. Now let's use the element in a circuit. Start by creating a new schematic in Eta Designer. We want to create a whole buck converter around the controller we've just defined. Start by choosing Place from File from the Library menu. Then find the library we've just created and click OK. We now see a list of available modules from the selected library. Since this library just contains our PWM module, there's nothing else to choose from. We'll click OK to place our controller. Now that we've placed our controller, we can edit its parameters. First, change the switching frequency to 250 kHz and select the voltage and current waveforms to be saved. Now, we can draw the converter around it. We'll start by adding the input voltage source and wiring it up. Then we'll add our power stage, 2 MOSFETs, an inductor, the output capacitor, and the output load resistor. We'll then wire them up. We'll define some of the part values. Set the power inductor to 4.7 microhenries, the output capacitance to 47 microfarads, and the load resistor to an expression of Vout divided by Iout. Now we'll specify these design variables. We'll add 3 variables. The first one is Vin, the input voltage, for a default of 16 volts and a range from 10 to 40 volts. The next is Vout, the output voltage, set to 5 volts. The last variable, Iout, or the output current, is set at 2 amps, ranging from 10 milliamps to 5 amps. Okay, great. For measurement purposes, we'll now add some node labels for SW, Vout, and Vin. The next step is to define the inputs and outputs of the converter to be used later in efficiency calculations. We'll set V1 to be an input and R1 to be our output. Now it's time to add the compensation network. We'll be using a PID, or type 3 compensator here, for the voltage mode buck converter. We'll now add the resistors and capacitors in the feedback network and wire them up. Now we'll set the values of these feedback components. I'm not making these up as I go. I've already selected the component values based on a compensator designed using the new schematic wizard and the controller tools in Eta Designer. Take a look at our other videos to see how this is easily done. Now I'll just finish setting the component values. Okay, now that the circuit is done, we can run a transient simulation to try it out. The simulation is finished. I'll now select signals to look at. I'll choose the switch node voltage, output voltage, and inductor current. Here we have our startup ramp. Remember that we've set it to 200 microseconds. Let's expand the simulation to 500 microseconds. Okay, now here's the full startup transient. We see the output voltage rising smoothly and settling at the desired 5 volts. We also see the inductor current doing what we expect. We can also view signals inside the controller. First, we'll create a new panel to separate the signals from those we've already shown. Then we'll open the Subcircuit schematic and then click on the View Waveform tool in the plot window. Now we'll click on the PWM ramp and the error amplifier output, as well as the PWM output to view. In the plot, you can see the controller operating as expected, with the PWM output toggling each time the error amplifier output crosses the PWM ramp. Now that the converter is doing what we'd like, we can look at the other analyses. We can start by looking at the steady-state waveforms and select the switch node voltage, input and output voltages, and inductor current. Here are the steady-state waveforms of the converter. We can also analyze the converter further by examining efficiency and the loss breakdown. Start by defining real component models for all power stage components. We'll simply choose an inductor model here for brevity. Now we can view the loss breakdown of our converter. This and other simulations are covered in detail in our other videos. To wrap it up, the Subcircuit capability and new analog and digital controller blocks make it easy to model your own PWM controllers or replicate an IC controller in Eta Designer. These subcircuits can be exported to libraries to use in all your designs or to share with your colleagues. I hope you've enjoyed this video and have learned how to use Eta Designer to create reusable controller blocks and examine the operation of your power converters. Please check us out at etadesigner.com to download a trial version and to view more videos like this one. Thanks.